Good afternoon, everyone. We're gonna quickly pick up where we left off last class. There was one last thing that I was gonna show. So just as a quick refresher, if you guys remember, we learned about stepwise regression last time, and in the code, we were doing this manually, and so we came up with this. We came up with this sort of set of for loops to basically program stepwise regression manually, and we saw how to calculate at the very end the outer loop AIC, BIC, and adjusted R squared to let us pick the model. Okay, but you normally wouldn't have to do it manually, so just wanted to show some of the functions that can do this kind of for you. And the way that you run this is you actually start off, you run your regression model against all of the variables that you might want to conduct the stepwise regression in. And so model, we have balance, tilde, and then dot. So when you put a dot there, that actually just means to regress against all the variables in the data set. Okay? And so.
Wait, when you put a dot where?
So here in our formula equation, where we have y regressed on x, instead of writing out all 10 variables, I could just put a dot.
Sorry, are you recording?
Yes, it is recording. Okay, and just to show you guys, I can go here, summary, model, and this should be the model that contains all of the variables of interest, right? And so we had 10 variables, which we can see here. Okay? Okay, and if I want to do stepwise, there's a function called step AIC, and you put in the model. I'll put direction equals. So you can put in backwards, forwards, or both here. And then this will give us the best one according to the AIC, going both backwards and forwards. If I run this, it'll look something like this, and it tells us that, let's see here. Okay, so we can see running on all of these variables, it will iterate through until it arrives. So this one is going backwards to a final one before it stops based on the threshold of the AIC. And if you wanted to do the BIC, it's the same thing, except we add an additional parameter here for K, which is the penalty term. Yes? Yeah, so this is in, I believe in the mass library, so you need to install this package first if you don't have it.
Mass, like mass package.
Yeah. So you do install.packages, quote, mass, and then you should be able to load it into the library. So if you guys remember, the main difference between the AIC and the BIC is the penalty term on the number of parameters. So we can emulate that by just taking the log of the number of parameters, which is just our, there's a modification against the n, the number of data points in here, and this is the modification that'll give us the BIC. So if you run this, your final one will look actually slightly different. It actually prefers fewer explanatory variables. Okay. Yeah, so I'll just kind of rush through this, and I'll update the notes for lecture 7 so that these last couple lines are in here. It's basically the automated way of doing what we had done sort of manually. But so this isn't a total black box. And the values might be actually slightly different because of the way this calculates the penalty parameter, but it shouldn't come up with an answer that is different. Okay. Any questions before we start today's? Okay. We'll jump on over to the notes. Pull this up. Okay. Okay. So lecture 8 notes. Right, and so last class we talked about kind of what is deemed as classical methods of subset selection, which is stepwise regression. And today we're going to talk about some more sort of modern methods, and these might be more common in some like machine learning regularization approaches. So we're going to be talking about a concept known as shrinkage or regularization. Okay. So we are going to, let me make sure I have this straight in my head. It's ridge first, yeah. So we're going to talk about three types of regressions. We're going to start off with ridge and lasso regression. Okay, so if you guys remember, we have our residual sum of squares, right? So this is if you square all of the error terms and add them all up, we want to minimize this with respect to all of our betas, all of our parameters, right? And so looks something like this. Okay, so hopefully this looks somewhat familiar to you guys, right? But the whole point is, right, it's yi minus yi hat squared. When you sum that all up, that gives us the residual sum of squares, right? So our observed minus our predicted, and our predicted is equal to, y equals beta 0 plus beta 1 x1 plus beta 2 x2, right? So this is our sort of standard equation. And the ridge and lasso regression are going to modify this equation in kind of a clever way, right? And so, again, we are trying to minimize our RSS by playing around with the values of beta. But now we're going to add an extra term. So minimize with extra term. And that looks something like this. Lambda times our betas squared. Okay? And this lambda is called our tuning parameter. Okay, so this ends up looking like this. Minimize our RSS plus lambda pj equals 1. And this term here is known as our shrinkage penalty.
Is that J equal R? Under the summation?
J equals 1, from 1 up to p, where p is the number of parameters that we have. But I guess I could write k to be consistent with everything else that we've written so far, so I can write k here. Okay, so what's going on here? How do I get rid of these things? Okay. What happens at lambda equals 0?
Nothing.
Yeah, it reverts back to our linear regression, right? It's just, you get rid of this whole extra term here, and then you're just minimizing your residual sum of squares, which is what we're doing for our linear regression. Okay. And actually, let me write out the full thing, because that, I think, helps conceptually. So, yi minus beta 0, j equals 1 up to k, beta j xij, plus lambda sum j equals 1, k. Okay, so normally, so forget about the shrinkage penalty for a second. What happens when my betas generically get kind of larger? Let's say we're starting from 0 and we increase the size of the beta. Right, and so you're subtracting from yi, right? And so as beta grows to a certain extent and multiplies against x's, it shrinks yi, right? And you want your betas to get to a point where it's kind of getting you as close to 0 as possible, right? Which is, you're trying to reduce your error, right? So if you remember in yeah, so think about it like this. I have something like this. If my beta starts at 0, I go like this, and then I increase my beta a little bit, and it goes like this, and then I increase my beta a little bit, and it goes like this until I get to here, right?
Does this process increase all of the betas, or just one at a time?
Well, it's an optimization. It'll do them all simultaneously, but I'm just illustrating the concept here. Suppose that there were just one beta, right? So really, you want these betas to converge towards some value where you reduce your RSS as close to 0 as possible. Okay, so what happens over here? So the betas are now increasing, and now, how does that affect the optimization for your RSS? who can help me out here. Yeah.
Well, since this one, if the beta's increasing, you get a more negative number, right?
Yeah.
Closer to 0. But on the left side of the tuning, as beta gets bigger, that value becomes bigger, so eventually they'll probably like cancel out or get pretty close to it.
Yeah. So the end result of this is that really, so these betas, so the betas that have an important effect will try to stay close to the true value. Whereas the betas here will shrink. So suppose you have a beta value that when it multiplies by x doesn't have a really big effect on subtracting away this I, or this y from this y to get you to 0, right? Then you're just increasing that beta for almost no reason, and this part will become larger. And so unless you can counteract the effect of it actually subtracting away from the yi, then you're increasing your penalty term without like a benefit to actually reducing the overall error, right? So this addition will artificially shrink our parameters that we deem kind of not important, not able to reduce the errors. And so, yeah.
When you say the betas that are important and the ones that are not important, I thought they were the same beta. So how do you, like, how is the one on the left important and the one on the right not important?
No, they are the same betas, but I'm saying if you had like beta 1, beta 2, and beta 3,
Yes.
If you were running a linear regression, and all of those betas will go in, if you're just running the linear regression with beta 1, beta 2, beta 3, and those generate some values, though the ability of specific parameters to reduce your residual sum of squares may be more important for some and less important for others, right? You can imagine like, for example, in our wage example, right? Your age was more important to help determine your wage than your height, right? And so when we do, so the relation to stepwise selection is that we would run through those one by one and then figure out, okay, height maybe is less important than these other ones, and so that one might drop out. In this case, we keep all of them in here, and the ability of height to reduce your error term in the wages example might be kind of small, right? But it still shows up here. And so this will actually say, okay, let's just shrink the coefficient that's associated with height, because it doesn't seem to make a really big difference with my residual sum of squares. Yeah. And in that way, it's doing something analogous to what we're doing kind of manually with stepwise selection, right? It's basically identifying variables that are less important and trying to shrink the effect of that variable away. And the extent to which that shrinkage happens is balanced against the ability of that variable to influence your residual sum of squares.
So how does it know which betas are important, just by how they affect the residual sum scores.
Yep. Exactly.
What is the so there's some numeric method that's marching the betas up and down.
That's
What's that actually doing?
That's the optimization. So the idea is, yeah, I mean, this is more fundamental with the linear regression, right? But if you, if we were to solve this numerically, right, in like a gradient descent, you know, it's like finding the place where the slope is as close to 0 as possible, right? And so it's doing without getting into the math, it's doing a specific search procedure to arrive at the best betas, right? And in that analogy, in this particular case, your ability to get to the flat area of the slope via certain betas is kind of less than one way to think about it is it's kind of less than the influence of this penalty parameter. Okay, what else was I going to say? Oh yeah, and then there's one free sort of parameter here, right, which is lambda. And the lambda value is really the parameter that you choose to set that gets you to decide how important the penalty is or how not important the penalty is. And so if you can imagine if lambda is really, really large, then that can overpower any values of these guys. So let me ask you, let's say lambda is extremely large, and that forces all my betas to 0. What would we say about the complexity of the model if all of your parameters are set to 0?
Very low.
Yes, that is a low complexity model. So setting lambda at a high value means that we are trying to reduce the complexity of the model, and setting lambda equals to 0 means I literally have all of the explanatory variables in there, which is the opposite, right? That means the model is like as complex as possible, right? So now the question is, how do I decide what value of lambda to pick? Yeah.
Sorry, just wanted to
Oh,
go
yeah.
back.
Mhm.
You said setting the lambda to a high value means that we're simplifying the model?
Yeah, so if you think about it, right, let's say this value is like 10 quadrillion, right?
Like make that value here.
Yeah, so even though these prefer, I need to change my sleep settings on here. So even though these prefer to have like some slope, right?
It doesn't matter.
It doesn't matter because this part is too big. So it's like, forget it, let's just go to 0, right? Yeah, and so the idea is basically like when your lambda is really big and you've reduced the model to essentially have no values, then we consider that to be a really simple model, right? Yeah.
Beta 0 is the intercept,
Yeah, yeah.
but why are we including that in the first
Oh, I guess this should probably be starting at 0. Why do we include this?
Mhm.
That's just
I just have
Yeah, right. In a linear regression, we include, you can include the intercept. You can actually exclude it too, but yeah. Okay, so back to my question. How do we decide the best value for lambda? What do you guys think? Right, a balanced value where you want it to have some kind of penalty effect, but then you don't want it to overpower.
Do you point an optimization algorithm at it?
What?
Do you point some optimization algorithm at it?
Kind of.
Set constraints.
Huh?
We set like constraints.
Not quite.
You test a bunch of them.
Yes. You could test a bunch of them, and how would you test them?
Excel.
Well, not like, I meant more theoretically. What would you be testing against?
I guess I could.
So I'm going to give you
What
guys.
would be an absurdly large lambda? Like 1,000? Is that?
Yeah, I'll show some practical examples of that. We typically vary lambda in like orders of magnitude,
Okay.
so like 10, 100, 1,000. But okay, I'm going to give you guys a hint. Anytime I'm asking you this kind of generic question, the answer is going to be the same thing that we've done in our previous examples, and for our future examples, it's always going to be cross-validation. Okay? So this goes back to our concept, right, of total error model complexity. And if our lambda is what did I say? So if our lambda is small or is large, no wait,
Lambda is large, then the model is complex.
is less complex. Yes, that's right. And then lambda is small. Okay. And so, yeah, Christopher's on the right track here. We can test a bunch of lambdas. And the way that I can do that is through cross-validation, right? I can test for the out-of-sample error, which is going to be what we're looking for here, right? And you'll find the value which gives you the lowest MSE, test MSE, and that's the lambda that you end up selecting. So just as a note, so ridge regression can be difficult to interpret. If K is large, so your beta shrinks towards 0, but doesn't ever get to 0. Okay, yes.
In such a regression, would you then, like after you get like the results of like maybe 10 betas, would you exclude the betas that are really close to 0?
No.
Okay.
I think that's why it's difficult to interpret, because
Yeah.
none of them do go to 0. You can't
But you could-
definitely say that factor doesn't matter.
I guess that's true.
Yeah, it's you couldn't generically say that, right? Because it also depends
Some
on.
might just have a small effect. But
Yeah, exactly, and it depends on the values of x as well,
Yeah.
in terms of its relation to the outcome. So you can't make that generalization. That being said, if you want to make your life slightly easier, too high.
So the above stuff with lambda, that's ridge regression?
Yes.
Okay.
So lasso regression is going to look very similar. So this is sum I equals 1 and yi minus beta 0.
On top of the
Oh.
summation?
That is n. I from 1 to n. Beta j xij squared. Okay, so that part is all the same as our linear regression. And then we add this guy again. But instead of squaring this, we take the absolute value. So absolute value instead of squaring.
And why is that easier?
Sorry, I shouldn't have said easier. Well, easier with regard to what you were asking for, because
Oh, because here they can go to 0?
yes,
Oh.
yeah, when lambda is large, betas will be forced to 0. But the values of lasso tend to be not as good as a ridge regression. So there's some trade-off there. But don't worry, we're going to talk about elastic net, which gives you kind of the best of both. But yeah.
But is like are there like values like for example you get better because you have more variables and then you like have this effect again with more variables, but then you get a better R squared or
Better in the sense that you typically will have better predictive outcomes on the ridge for out-of-sample testing. So your out-of-sample mean squared errors will tend to be lower with ridge than with lasso, but lasso gives you slightly easier to interpret results because you can actually just drop variables. Yeah. Yes.
For the summation of beta j,
Yeah.
your our constant in our decision variable, right?
Yeah.
Why is the j not starting at 0 to k as well?
Oh, because I have this thing.
Oh, you have written out. Okay, very good.
Yeah. So the logic, all the logic that I spoke through for the lasso regression is basically the same as the ridge regression, right? So, as your lambdas get large, then your model becomes less complex, and if it gets small, then the model gets more complex. And the only difference is this feature where your betas are actually allowed to get to 0. Okay. So, yeah, this is kind of like a more modern version of doing subset selection. Subset selection, I think, is easier for some people to kind of visualize because we're like literally removing variables. But the premise of why we remove variables and how we get to a particular model, right, is pretty much exactly the same here, right? We are doing this model complexity trade-off in order to balance between our variance and bias components of our error, and it's going to tell you in kind of a different way, rather than totally just dropping the variables, it's actually going to change the value of the parameters for the variables to get us to that kind of sweet spot, right? And in the same way that in subset selection, I can decide on which model is the best via cross-validation. You can decide here what the best penalty parameter is via cross-validation as well. Okay. Yeah.
Is it important to know like how this lasso regression forces betas to 0? Or just to know that it does?
Yeah, I don't even know if I could answer that. Yeah, just to know that it does.
Okay.
I can kind of imagine the math, but I could be wrong, so I don't want to, yeah, lead you guys astray here. Yeah, and actually, yeah, this is not going to have I don't think this has an analytical solution. And doing the math with absolute values is kind of a pain.
Okay.
All right. So let's jump over to the code. And we're going to start off, we're going to do the same data set as our previous example. So we're going to need to get ISLR. And we're also going to need GLMnet, which is the package that allows us to run ridge and lasso regressions. We're going to load in our credit data set and then set it up kind of as we did before.
What's the syntax to install library?
Install.package and then the name of the package in quotes.
There's a pop-up that's
Oh, sorry. So here, I'll write it out. So if you want to install it, you would do install.package glm. Is it install package or packages?
I think it's packages. Yeah, it never works for me if I type it in myself. I always miss the S.
Right. Okay. Yes.
4.1 half an 8, that's 7 out of 8.
Oh, 4.1-8 you mean? Oh, the version, yeah, yours is probably a newer version than mine. Yeah, that's fine. I don't imagine that that's going to make a difference. Okay, so, oh, you know what? I'm going to, apparently I'm doing this in data tables, but sorry guys. I put in the data table package. Yeah. Yeah, for part of this, I'll actually ask you guys not necessarily to follow along. But for now, you can follow. Okay, so yes, sure. I'll make this part a little smaller.
So you're just taking out all the names except for ID and balance?
No. Okay, let me explain what's going on here. Yeah, I think this part I was intending you guys not necessarily to directly follow along. I'm putting it in data table for some reason later on, I think. What this line 11 does, ID colon equals null, is a data table operation which just drops a column. Basically all I'm doing is dropping the ID column, right? Because that's not going to be useful in a regression. In 13, this is actually something that you guys should all be able to do. What's happening here is I have balance regressed against, I have a dot there. What does dot mean?
It's like at all.
Yeah, you put in all of the variables. Plus 0, does anyone know what this means? This means that don't include an intercept. Okay.
Oh.
Yes.
There's a data table package that we need, right?
Yes.
And it's not linear.
No, it's called library data.table. So you'd also have to install that package if you don't have it. Yeah. So this is the linear model that we're used to. I'll keep it there for now. We'll look at some of those results a little bit later. And I'm going to do some data preparation. To prep it for running the ridge and lasso. So that's what this, that's what lines 15 and 16 are doing. I'm essentially putting all of my data into a matrix, a model matrix that's going to look something like this. So this just preps the data. It turns like the categorical variables into columns. And then I have this -1 to drop the balance column, which I've initiated as my response variable in this way. And then y is just a vector of those values.
So you need balance in there so you could have a, what's it?
This is just a shortcut so that when I do the -1, the balance was at the front. And that was the one that got dropped.
Why didn't you just drop it before when you dropped ID?
Because then this wouldn't work. Kind of makes sense. It's janky, but the idea is X, you want a matrix of all of your explanatory variables, and then Y is the vector of those of your explanatory variable values. Okay, so ridge regression, GLM net, X is equal to X. So we don't have the Y tilde X thing. You literally have your X's input as a single object in a model matrix, and then your Y as a vector. We'll have alpha is equal to 0, and lambda is equal to 0. So alpha, so ignore alpha for just a second. I'll explain what that is. Lambda is the value of our tuning parameters, what we've been talking about, right? And so when lambda is equal to 0, then the ridge regression should look like what? A normal linear regression, right? And so we've run our linear regression, and we can compare it against our ridge regression. So if I do summary linear, we get, you know, our typical regression with all the values that were estimated when we put in all of the variables. And for the ridge regression, if I type in ridge, ridge, I think it's coefficients. No. All right, hang on. I have it somewhere here. It's beta. Ridge, dollar beta. You should see that these values should basically match the coefficients that we derive from the linear regression values. Okay. Okay, what's alpha? So alpha is a second parameter that we haven't talked about yet. This is actually a way to go in between your lasso and ridge. Okay, so you can think of, there's an extra parameter where you have both of the lambda penalty functions, the absolute value one and the squared one, together, and then there's a parameter that as you increase alpha, it will prefer the penalty term of the lasso. So if I set alpha equal to 1, this becomes a lasso regression, and at 0, it's a ridge regression.
So 0.5 is this both?
Huh?
0.5 would do both, kind of?
Kind of, yes. And is there a point to that? Yes, we'll get to that. There's the secret weapon, which is the elastic net regression, which is both a ridge and a lasso, and it gives you kind of the benefits of both. But we're going to talk about that later. So for now, just think about alpha equals 0 means you're doing ridge, alpha equals 1 means you're doing lasso. Okay, great. And so you can see, right, that as I was saying, lambda equals 0 equals our linear regression, and we get the same betas as in our linear regression. I think I'm pretty sure they should be exactly the same, 426.
They are. The first one is, but the mid and ratings are not.
Male and female, but the ridge one only has female.
Yeah, but that's, wait, are there more than? Oh no, that's still, okay, it's very close. Since there's no intercept, right, the interpretation of our dummies is actually a little bit different, but you can see the difference between male and female is about 10, which is reflected here. Yeah. So these will be quite, it's not going to be exactly the same because, yeah, it's still, it's doing this iteratively in an analytical way, but they'll be very, very close, yeah.
Is it possible that we do different numbers? Or we should be doing the same numbers?
With this, you should be getting the same numbers. Or almost the same numbers, I guess. Yeah, but the termination for it should be very, very similar, if not identical. Yeah.
I'm confused on why you don't have the intercept in the linear regression.
I did that because in the default setting for ridge and lasso, there's no intercept.
Okay.
And so I removed the intercept from the linear regression so as to match
Okay.
what the ridge and lasso do. Yeah. Okay. So picking the optimal lambda, so which lambda gives the lowest test mean squared error, right? And so 1, select a value for lambda. 2, perform a cross validation, right? So you could do like k-fold. 3, obtain the average test mean squared error. 4, repeat steps 1 to 3 across a range of lambdas. And 5, select the lambda which yields the lowest average test MSE. Okay? And so I'll show us how to do this manually in a second, and then we'll see the sort of built-in way of doing it. Okay, let's take a quick 5-minute break. Use the bathroom. Hey. Sure.
Verifying my interpretation.
Sure.
So, in seeing in this like interaction variable, interpreting this, what I thought was that even if the base level changes for example, the interaction factors, that the model prediction or like the conclusions we arrive to won't change because the relationships involved in the data that we're modeling for still remain the same. It's just that we're coming to it in a different way. Like the values might change.
Yeah,
but
that's
the
right.
Overall thing. Okay.
Yeah.
Okay, good. And in terms of like the other considerations we should have made, I was thinking that this is missing MSE, and that might be something that would be valuable. Are we thinking about other parameters we could add, or are we thinking about like general model?
Yeah. So you can talk about things generic to like the regression models, and then you can talk about things specific to that model. So the setup of the variables, the data itself, either is okay.
Okay.
Lack of an MSE is not like inherently something wrong with it. You could like calculate it, right? It's what assumptions are baked into the model that might make it wrong, or what are issues with the data that might make it wrong.
Okay, that makes sense. Thank you. And just one more question.
Yeah.
For the constant, I know that this is supposed to be,
The intercept,
our intercept, but is this in relation to our just our interactions?
It should
Or-
be in relation to all sets of
okay.
categorical variables.
Okay.
Right, and so
Yeah.
there's something that's going to be dropped in each one, and you want to make sure that that constant represents that base level for
Okay, gotcha,
each
gotcha.
categorical
For each
variable.
categorical. Okay,
Yeah.
thank you so much.
Uh-huh. Hey.
For tomorrow, officer, I need to send you email for scheduling sometimes.
Okay.
Or is it possible that I go to the office hour or something without previous email to you? Because I want to talk about my project.
Yeah. You can come to office hours, or you can send me an email, and we can meet at another time.
Okay.
Yeah.
No, office hour is fine.
Yeah.
But, before office hour, I don't need to send an email.
Up to you. Either way is fine. Yeah. If you want me to look at something beforehand, or if you just want to explain it to me, whatever you want.
I can send some, because I did some EDA
Okay.
analysis based on one data set that I found.
Okay.
So I can send that to you.
Yeah.
And tomorrow we can talk more about the details. Yeah.
Sure.
Thank you.
Uh huh. Hey.
When I installed the packages, but when I call the credit, it says that the credit doesn't exist.
Oh.
I can't access no.
Hold on. Let me see. Okay. So that works. That works. Okay. And then run this. Yep, there it is. So you've loaded in credit, and now could not. Oh, names. So this is S.
Oh.
It's names. Yeah. Run this. Invalid. invalid type arguments.
Yeah, it's very.
Let's see.
Yeah,
I don't know, I feel like still the majority is.
You want to do,
yeah, about half of students have an engineering background, but I have not done any engineering design while in ag. I kind of miss it. honestly,
okay.
But I like it.
Oh, you also need data tables, so,
Do advanced federal.
yeah.
That's not what I'm into.
Yeah, sure, that makes sense.
Oh, then probably you don't miss it.
You know.
Okay.
How about you could do something like that?
And then I'll add that as a library.
For ag.
You know, there's a lot more to engineering than thermal.
Okay.
Sure.
It's a good group. It's a little.
You'll want
it's
to
challenging to navigate because
load this in as a data
I
table,
feel like the
so
guidance
interdisciplinary.
credit,
guidance regarding
data table,
Yeah,
credit.
it's garbage.
Okay. So this will transform credit into a data table, and this ID colon equals is an operation that's in data table. So this has to happen before, not after. So I'll delete this one. So now that I run this, that should work. And then these should all work. You have capital. Yeah. So we'll run these again.
Yeah.
There you go.
Thank you.
Yeah, no problem.
And I kind of know like what I'm doing in the research, so I know what I kind of think is valuable and whatnot. Yeah, I guess stuff like that.
Okay, let's get back to it. I am gonna copy and paste a big chunk of code here. So this part you don't need to directly follow along. But let's talk about what this is doing. Okay, so I've created a custom function called kfold cv, kfold cross validation. So hopefully this will look a little bit familiar to you guys. So I have an index, sample 1 to the number of folds, and I do that a number of times equals to the rows of my input with replace equals true. Does this look familiar to anyone? Yeah, so this is, if you remember, when we built a k-fold cross-validation manually in class, right? So this is the part where, let's say I have 100 rows and I want to do a 5-fold cross-validation. I'm going to assign each row a random number 1 through 5 by sampling 1 through, the number of folds. And then I set up a training test set, from my original data set, I create a training set for X and Y, where they don't equal the index right value in my for loop, and then I generate the testing set where they do equal that index value, right? Hopefully this all looks somewhat familiar. And then at this point in the original one that we had created together, this was running a linear regression on our wages example, right? We tested one with age and one with height, I believe. Instead, I'm putting in our ridge model. And I'm leaving lambda as a generic value that I can input as an input of my function, okay? Run the regression. I'm gonna do some predictions out of sample, right? Because I'm going to predict it based off of my test set. And then I'm going to generate my out of sample mean squared error by doing those predictions, taking the observed values from the test set, subtracting away the predicted values from that model, scoring them, and then taking the average. So that's my mean squared error. And then I'm going to store that. Okay, what's going on here? Okay, yes. This part of the function is a little bit different. I'm actually going to store every single model that I run. And the reason why I'm going to do that is so that I can show you what happens to my coefficients as I vary lambda. So we'll see a plot of that a little bit later. Okay, so I'm going to run this guy.
So that function doesn't change lambda on its own, right?
No, it does not. This is the part where I'm varying lambda. So I'm going to check a bunch of lambdas. So my for loop is going to check lambda in 10 to the 0 up to 10 to the 4th power in increments of 0.1. So it'll do 10 to the 0, 10 to the 0.1, 10 to the 0.2, all the way up to 10 to the 4th. And those are the lambdas that I'm going to test. I'm going to put that into my regression, kfold.cb, which is the custom one that I made, putting in my credit data set. We're going to do a 10-fold for the k-fold. We're going to have k equals 10. We're going to put in those lambdas, and we'll have alpha equals 0, so we're doing ridge regression. And then I'm going to put all the models together.
What is the L again?
The L is lambda. Yeah. So I am testing a whole range of different lambdas in my cross-validation procedure. So I will run all of this.
And enter ridge equals alpha 0.
Yep. It's ridge because alpha is equal to 0. Okay. And it'll look something like this.
So lambda 0.
Yeah, so I could actually probably go down this way. But the idea, right, is that what happens when your lambda is really large is the model simpler, right? And so in our traditional plot of model complexity, where it's simple to more complex, it looks like this. This is actually kind of like flipped, right? And so, yeah, these values are pretty small, and you want to get something that minimizes your test mean squared error.
So low lambda is always better.
Huh?
So low lambda is always better.
Well, it'll usually go back up, right? Right? So very fundamentally, we think about the bias variance trade-off, right? And so as you decrease the size of your lambda, you decrease bias, but you increase variance. And as you increase the size of lambda, you increase bias, but decrease variance, right?
But this basically tells us that like we shouldn't basically that the normal linear regression performs the best, right? In this case, or am I understanding this wrong?
Lambda of 10 is best, but that's the lowest.
Oh, 10. Yeah, true. Yeah. Stupid.
Yeah, so
Yeah. No, that makes sense.
the one issue is that like we're doing like the log values, so the errors, it's hard to see the differences when you're like in this range. But if I were to zoom in here, I think the curve actually does look a little bit more sort of parabolic in the way that we're used to, right?
Would you mind zooming in, kind of testing
I don't, but,
-1 to 2?
the problem is that I would want to test a better set of of lambdas, and I don't know, like, off the top of my head if I'm gonna be able to arrive at, because it's in like this exponential way, if I'm gonna get the right values. But instead I'm gonna show you that the automated way will actually do that for us. So we'll be able to see maybe a different version of this in a second. Okay. The other thing that I wanted to show you guys is the coefficient values, how those change as we vary lambda. So we're going to do that here. Oh, of course. All right. Okay, so this is a very typical plot that you might see for a ridge regression as you vary lambda. And we'll note, right, that when lambda equals 0, that's when you have the same thing as a linear regression. And if you look closely at these lines, you will see that the lines all will start to converge towards 0 as your lambda gets larger and larger, right? That's what we expect, right? The penalty term goes up, the betas start heading towards 0. But what do you notice about when each parameter will start going towards 0? Are they all happening at the same time? Right, so you can see this purple line and the blue line right at the bottom. There's two lines. One of those lines starts heading over to 0 a lot sooner than the other one, right? So that is, in essence, the power of the ridge regression, is it can really hone in on which parameters you should get rid of first, right, in order to still get the like positive effect of reducing your residual sum of squares, right? And so here, this blue line, so let's say, I think that's gender. So it's, if I look at purple versus blue, so gender female versus married, right? Essentially, it's saying that my ability to reduce my test mean squared error, in other words, my predictive ability on out-of-sample testing, I want to preserve this marriage variable more than the gender variable, because you can see the gender one starts going up to 0 first before the marriage one does, right? And so marriage is more important of a variable in the sense that it probably allows the model to get better predictions than gender. And in a similar way, I can also look at like this pink and green line, right? This, or is that like magenta, I guess? That one goes down, and the green one stays large, not larger, it stays flatter for a longer time before converging to 0. So the number of credit cards, which is green, versus my ethnicity. So in this case, if I wanted a model that would, again, predict my credit balance, the variable of the number of cards I have is probably more important than my ethnicity. Yeah. Yes?
So then this helps inform model selection, because then you could drop variables and make it a simpler model, or?
Well, you might expect that variable selection may follow a similar pattern as this in terms of which ones start going to 0 first, but that's not the intent of this, right? This in itself, built in, is doing the the balancing of your model complexity that you're trying to do with subset selection.
So that itself would be
Yeah.
the.
And the whole idea here is instead of dropping a variable, I just want to figure out what the best lambda is.
Okay.
Where my lambda is to give me the best predictions.
Okay.
Yeah. And whatever that is, whatever slice of lambda is, those would be the coefficient values of your model. Yeah. Any other questions? Yes.
So, wait. When you're comparing two variables,
Yeah.
and seeing which one converges to 0 first,
Yeah.
can we do it like the one below the actual 0 and the one equals positive?
It's not so much the distance from 0, because then it would look like this one would be way better, but that's not necessarily the case. It's about which one starts to head towards 0 first. Yeah.
Wait, which is this tipping point or this tipping point the important one? They're two like.
It's a little bit of both, right?
Yeah.
And it's not like, it's also not linear, right? So, yeah, but luckily you don't have to like really think about that, right? Because all you need to do is figure out the right lambda and you're basically good to go. But it's kind of interesting to understand the meaning behind the pattern, right?
Yeah.
So.
So will you be able to decide which lambda to use based on this graph?
No. You would decide based off of the mean squared errors, yeah. So if I manually went in and looked, the best lambda value, according to my sort of manual way of doing it, is about 1.25. And I can run this, and we can look at the ridge coefficients, ridge beta. 1.25.
Oh, actually, I thought you were going off the plot.
I think I just looked at the actual values. And then if you look, actually I don't even know why I put this here. All right, forget this. Anyway, so this is one way that you could arrive at your sort of best lambda. We can also do this for lasso in a pretty similar way, right? And I'm gonna copy and paste basically the identical thing that I did for ridge. Here I'm gonna test a set of lambdas from 10 to the negative 1 up to 2 by 0.1, and then I'm gonna run my k-fold CV, right? But the one difference being that my alpha is equal to 1 as opposed to 0. Yeah.
Is there any reason that you chose a different lambdas? Or?
Yeah, the range of lambdas that I searched for, I think, was just to make it so that the graph looked nice. Yeah,
Okay.
basically. Yeah.
But this is just to help us determine what lambda to choose, right?
Correct.
So
Correct.
then,
Two vectors
Since-
together and one.
the biggest range, I guess, for log lambda compared to coefficient value is that this big blue line, right? Why wouldn't we just get rid of all the other variables and just use that one?
Because, yeah, you're talking about here,
Yeah.
so be very careful. This line here, the fact that it's the largest, the size of this relative to 0 is not an indication of how important or anything a variable is, right? Because you could imagine that, in fact,
So would it be better to get rid of it then?
no. It's all about, because the parameter size could be a function of the values of x's, right? So if your x's was like on the order of, if you were regressing something on like age, height, weight, and like millions of dollars, right? If the x value has $1 million thing here, then your coefficient might be really small, right? So it actually depends on other aspects. So don't be, don't get hung up on the size of the coefficient. It's all about, kind of generically how it goes towards 0. And it's kind of hard to compare this one versus these ones because,
So like, would it be fair to say like the best lambda to choose would be like log lambda 5?
Oh, no. You can't choose from here. It has to be based off the mean squared errors.
Okay.
This is just a demonstration of what it looks like as we change lambda.
Okay.
But to actually know what lambda is correct, I want to go back and look at my cross-validation results, figure out that, oh, this one has the best MSE or this one has the best MSE, and then choose those values.
Okay.
Yeah.
Are there cases where when you try to run the MSEs and compare to, I guess, the convergence to 0 part of things, this graph shows like the complexity of our model in a sense where we have a lot more variables merging to 0?
Yeah, I guess in to some degree, yes. Right, so here is less complex, and there is the most complex, because you are basically saying that there are very many variables that are influencing your model, whereas here you're saying there are not so many, or that variables have less influence on the model. And so that's kind of leading to that model complexity, because the ability of a parameter to affect your model is more muted when you have a larger lambda.
And by doing the cross-validation with the MSE, we will find the sweet spot.
Yep.
Where we're on that graph.
Exactly.
And what if we're not happy with like it's too complicated to be like presented or something like that.
Well, so once you've gotten a lambda, then you have your coefficient values in the same way that you would in a linear regression, right? You would have 10 coefficient values, and then you could present that as like your regression table, right? In the same way that you would with a linear regression. Yeah. Okay. So I run this. Similar type of thing with the values of lambda and your mean squared errors. And then same type of thing here. Let me zoom. Okay, so here, the big difference, right, with lasso is that instead of asymptotically approaching 0, when you have absolute value, it actually allows the value of the beta parameter to actually arrive at 0. And actually it'll be a little bit easier to see here, right, when, in what order different parameters hit 0.
This is lasso?
Yeah, this is lasso, right? And so here, I look here, and I can see this pink line gets to 0, and then this magenta and purple line get to 0, and then blue gets to 0, then green gets to 0, then red goes to 0, and then eventually this blue one will go to 0. And you can roughly kind of say that the variables in the ridge will kind of follow in that pattern. It's just kind of easier or cleaner to see here. they get dragged to 0, and let's say I were like, if my optimal lambda were right here, then anything that's at 0 is basically a dropped variable, right? And so this is actually doing a more like complex version of your subset selection for you, right? It's actually dropping the results, but it's also modifying the values of the coefficients as well. Okay, so same thing, except I'm allowed to be 0. And as I mentioned, we typically think of the ridge regression as maybe a little bit more robust in the sense that the predictive outcomes are a little bit better when you're not forcing these things to 0. But the interpretation of this is a little bit cleaner because it actually lets you get rid of some variables. Yeah.
Like, what does mean a little better? Like, what, like, kind of like.
Well, I mean.
What are we talking about? Like, what kind of frequency? Like, usually, like.
Yeah. So what I'm talking about is the test mean squared error values for ridge tend to be lower on average than lasso.
Is there like
Well, that's,
how much?
no, you can't generalize really because it depends. And in some cases it may actually do worse, right?
Okay.
But on average we would say ridge is better. And there's like more complex reasons to think about why you do one over the other. But I think this is all kind of like leading up to ElasticNet, which kind of lets you do both. So you kind of get the best of both worlds.
So what is the ideal lambda according to ridge and lasso?
Well, according to,
Did it find it?
yeah, well, I did it kind of manually over that search space, and then I just picked kind of the lowest. But if you actually want to find the best one, let me show you. Ridge best. So we're going to use GLMNet again, but in front of it we're going to do CV. Okay, what does CV stand for? No, cross-validation. Okay, and so x equals x, y equals y, alpha equals 0, and then the metric that I want to use is set via a parameter called type measure, and I want to look at the MSE. Okay?
Why didn't we start with that?
Because you have to know how this actually works first. I mean, I could teach everything to be a black box, but you know, I don't know how much you guys would. It's all a balance. No, lambda does not need to be here because we are searching for lambda. We do not want to set a value for lambda.
Not even like an initial value?
Nope. Looks something like this. Yeah, in this case, the shape makes it look like the lower the lambda, the better. It's not always the case that it will look like this, but you know, also finding like a data set for class to like, it's challenging sometimes to get the right, prettiest examples. Okay, so this will do, I think, the same thing as my, oop. Yeah, I did zoom already, yeah.
Is there a way to just give me the best lambda as a value?
Yes. We'll get there. These are the coefficient values heading to 0. We saw this already, but it can do it automatically for you. You don't need to like whip up a fancy chart. All right. Hold on to your horses. The way you do this is GLMNet, x equals x, y equals y. Once I have run once you've run line 85, which is the cross-validation procedure to find your lambda, then you can do this. Lambda equals ridge.best dollar lambda dot min. And that gives you your best lambda. Okay, punchline, there you go. And I run this, and we can look at, for example, ridge.auto dollar beta. There you go. And wait a minute, what's happening here? Is that, wait, I don't have it backwards, right? Oh. Alpha equals 0. Okay, whew, I was about to be like, oh shit. Okay, sorry, what was your question?
What's the default if you don't put in alpha equals to 0?
I have no idea. That's why I was about to freak out.
Probably just find its own best alpha too.
It's got a lot of variables.
I'm not actually sure. Yeah, I wonder if it actually the default is 1. Well, we can see in it in a sec. Okay, so there you go. And now you have a new set of coefficients that are now different from your linear regression, but this will give you better predictions. Like, what do you guys think? If I were to run a linear regression and I were to do subset selection, dropping certain variables using stepwise, versus doing this procedure, doing a ridge or lasso, which one do you think gives you better predictive outcomes? Yeah, the ridge and lasso, by a lot actually. So keep that in mind.
How does the big O look like for the ridge and lasso?
Should be no different. It should be the same.
Oh,
Right.
but it doesn't take long.
No, well, I mean, it might take a little bit longer, right? But Big O cares about the order of magnitude, so it's about it's all about the size of your input for a particular model and how that affects your runtime. And so as your n and k increase, so your number of data points and your number of columns increase, your linear regression will increase in complexity in a certain way, as will the runtime of the linear regression will increase, but as will a ridge and lasso regression. But the optimization is the same, right?
Why would anyone do this stepwise regression in that case instead of like I mean, I get if you maybe want to drop some variables, but why would you not do a lasso regression instead of a stepwise regression?
Maybe you haven't invented lasso yet.
I guess.
Yeah.
Because at least like I haven't seen. Like, I've heard the name, but I've never seen anyone.
Yeah, but you've seen a lot of people do stepwise selection, probably.
Not really. That's true.
Yeah. Well, a lot of.
I just used to see the people doing like a normal regression, just.
And they just like choose variables because they're like, oh, I think it affects it in blah 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 way, and like, yeah.
I guess.
Yeah, I mean that. So I will say subset selection is handy in some ways that mainly have to do with like interpretability, right? Because now I don't have to deal with lots of variables, and it's a clean way that when I talk about linear regression and the results of a linear regression, like everyone understands like what's going on, right? Whereas here, these are like modified beta coefficients. They're not like directly.
I mean, the lasso regression still involves some variables, right?
Yeah. But then like your coefficient values are modified, right? And so those parameter values are not the ones that minimize your error terms, but they minimize your error terms in relation to this like weird penalty thing too, right? So part of that is the interpretability aspect. And so when it comes to interpretation, people like to preserve a lot of the sort of simplistic aspects of a linear regression. And so oftentimes you don't see these methods being used as much in like inference type models. You will see these types of models being employed a lot more in predictive models where you care about the outcomes, but then in predictive models, like you don't usually even show the coefficients, right? You don't even care what variables are in there as long as you're getting the best predictive outcomes. So we're kind of operating in slightly different like focuses, yeah.
What do you mean inference?
So,
Trying to figure out what factors are important.
yeah, so harkening back to one of the big themes of this class, which is kind of two approaches in regression that kind of diverge. So one is much more in the predictive world, and one is much more in the like inferential causal world. So in inference and the causal world, we care a lot about the effect of X on Y. So you want to know, like, as I change some values of X, how Y changes. Whereas in the predictive world, we care a lot about my ability to predict outcomes for Y accurately. And those are like, the way people approach modeling in both of these worlds is pretty different, even though, like, if you think about it, they could stand to benefit from each other in many ways, yeah.
So I guess an example where like lasso would be handy, and like if you're trying to infer something, is like if you have, I don't know, you're testing a bunch of different the expressions of a bunch of different genes, and you don't want to say that every single gene you're possibly testing is important for like the final outcome. You kind of want to identify like what are the key players.
Yes, I mean to that extent, it's like you're preventing the model from like overfitting, right? Yeah. Okay. Yes.
Sorry, could you quickly talk about why the predictive world and the causal world are different, why they diverge?
Yeah. So the techniques and procedures that I use to determine whether or not there's an influence of X on Y is different fundamentally from trying to guarantee the predictions are really good. So let me give a simple example of this. Okay, there's all of these little stupid examples. I need to think of one. Yeah, so let's say you want to predict the sales of ice cream from a shop, okay? And one observation that I can make is I can go outside and I can see how many people are wearing shorts, okay? And it so happens that when I see a bunch of people wearing shorts, the sales of ice cream is really good, okay? And so from a predictive standpoint, I could do really, really well just from observing people and whether or not they're wearing shorts, right? And in that sense, if all I care about is my ability to get good predictions, then a model that relies on observing people wearing shorts is a good one, right? If I wanted to understand why people are buying ice cream, then it becomes different, right? Now the question is, okay, what if I told a bunch of people to wear shorts? Would then ice cream sales skyrocket? Probably not, right? And so the causal inference world cares about understanding the thing that causes an outcome as opposed to the thing that lets me predict accurately. So in that case, it would be like the causal world would be like, well, it's actually because it's hot outside that people want to buy ice cream. And when it's hot outside, people also wear shorts, right? And so there's this whole different area that we're also going to get into in this class that thinks about these things. And you know, it becomes a little tricky philosophically too, because oftentimes the predictive ability of like causal models tends to be really bad. And it's like, well, how useful is it if my like causal models that I did all this work to demonstrate these relationships don't actually give me good predictive outcomes, right? So you actually care a little bit about both sides of these things when you, or you should care about both sides of these things when you're modeling, even if you're focused in one area more than the other. Does that example help a little bit? Okay. Okay. Where were we? Okay, we can do the same thing with lasso. Let me get rid of these. Okay, so this is the exact same thing I just wrote for ridge, but for lasso, all I have to do is set the alpha equal to 1. Okay, so as a refresher, right, cv.glmnet means run cross validation to figure out the best value of lambda. That looks something like this in terms of the mean squared error relative to my okay, yes, I remembered, sorry. Tangent, the reason why the plot looks like this is because this is the in sample, not out of sample one. But if you do the out of sample one, it should look more parabolic. Remember, if you do the in sample one, that is just looking at the decrease in bias, so that's asymptotic. I'm glad I remembered that. Yes. Okay. Okay, so this plot, this is the lasso version, so they reduce down to 0. You can run this with the best value of lambda, lasso.auto $beta, and here, do they not? Oh, well, hang on. What is the value of lambda? Lambda.min. Oh, lasso, whoops. .58, yeah, okay, so that's like here. So, so actually here, in this case, it hasn't actually dropped any of the variables completely yet. So that's why they are all retained in here. Okay, 10 minutes. Okay, we gotta, we'll go quickly here. Well, I can always spill over to next class, but yeah.
Are you going to talk about the in-betweens, like when alpha is in between 0 and 1?
Yes, we're going to talk about that right now. Why not both? So this is elastic net regression. So min, this whole thing, I equals 1, and yi minus beta 0, I equals 1 to k, beta j, or sorry, j, xij squared plus lambda 1, 0 to k of beta j plus lambda 2, 0 to k beta j squared. Right, so this is our lasso penalty. and this is our ridge penalty. So solve via cross-validation. For both lambda 1 and lambda 2. Computational complexity increases much faster. Compared to ridge or lasso. Okay, so this overcomes shortcomings from both models while retaining benefits. Okay, so keeps feature selection, quality from the lasso. So this means setting beta to 0. It's got the effectiveness of ridge shrinkage. So this is what I was talking about, right? With the ridge, the shrinkage tends to give better predictive outcomes, and it kind of retains that quality. And very good at handling highly correlated variables. And this is one of the important ones. So if you have a lot of variables that are correlated, they may have like similar types of effects. And so what tends to happen is that in the lasso regression, you just end up dropping certain ones when you have high correlations between variables. Whereas here, it kind of retains the effect of those corresponding variables without necessarily dropping them. So yeah, people have generally found that ElasticNet does much, much better at the handling of correlated variables. Okay, any questions? Okay, so, yes.
So if we have like a fair amount of variables, not like a large amount, we should always use the ElasticNet as long as it's like computational, like
Yeah, and actually, you know, the computational complexity of these things has been much improved since even since I first started doing like lasso and ridge regression, which back then it was, makes me sound really old, but I'm not that old. You know, back when I was first learning it, actually people would suggest limited use of ElasticNet regression, but the procedures and the training and computational power now is good enough that I don't really hear that limitation anymore. Yeah. Okay, I'm just gonna copy and paste this because we don't got a lot of time. Delete this. Okay, so line 100. These are setting specific training parameters for doing the cross-validation procedure. So this is going to be a cross-validation procedure that we're going to run some number of times using a random search for my parameters, which are my alpha and my lambda. And so alpha, when you're in between 0 and 1, it is a weight that gets assigned to your lambda 1 and lambda 2, essentially. So, could not find, oh my gosh, it's, that's right. We got to put in more libraries. Library mass and library caret. Okay, so elastic.net.best is a procedure to identify the best value of my alpha. So I run this, and you can see the sort of iterations that it runs through to calculate your alpha and lambda values. You can see it does take a little bit longer, right, but not that much longer. So if I run these guys, is that right? Yes. It actually looks kind of similar to the lasso one. Yeah, and I can run the models. The final model here, elastic.net model. All I'm doing is taking the best value of alpha and the best value of lambda from that training process before. So it's $best tune, $alpha, and then $best tune, $lambda for that training model. And then I can just to ask it to spit back the values of the coefficients. Yeah.
Can you show the alpha and lambda answer?
Yeah. If I wanted to do this, I could do best dot alpha, best dot lambda, and that's this guy here, and that is this guy over here. Run, best alpha, best lambda. So 0.958 and 0.0421, and these were the values that were actually printed at the end of the training thing, right here. So as it iterates through, it'll look through a bunch of different values of alpha and lambda until it arrives at the best one.
How does that compare to what we had just for the last one?
Yeah, well, that could be a good exercise for you to try to do. So what you could do is go, look at your ridge regression, look at your lasso regression, pick the best lambdas for those, and then look at your best elastic net, pick the best alpha and lambda for that, run them against a test set of data and see how the mean squared errors look like. And I can guarantee you that the elastic net will always be better than the ridge and lasso. So as far as predictive output, AKA your test MSE size, usually you'll be elastic net is best, then ridge, then lasso. Yeah. Okay, that's it.